November 1942, while MIT-trained petroleum engineers were designing complex carburetor modifications, trying to solve the fuel crisis that was losing the British Royal Navy the Battle of the Atlantic, an 18-year-old Canadian farm mechanic with barely a ninth-grade education grabbed a tin can, some scrap rubber, and a spring from a broken truck clutch and accidentally tripled convoy range in 3 weeks. How did a modification so simple that it cost less than 50 cents completely escape every engineer, every naval architect, and every fuel specialist in the Allied command? The rain hadn't stopped for 5 days. It had turned the supply depot outside Halifax into a freezing mud pit that swallowed boots and made every step a fight. James McKay knelt beside a stack of jerry cans, watching precious gasoline evaporate into the November air. Each drop represented another mile a convoy ship couldn't travel, another torpedo the destroyers couldn't dodge, another merchant vessel that would sink because the escorts ran dry before reaching safe waters, another convoy lost, another 100 sailors dead, another German U-boat that would live to hunt again. This is the true story of how an 18-year-old farm mechanic stumbled onto a fuel storage breakthrough that would extend Allied naval range and change maritime logistics forever. But on that freezing morning in Halifax, nobody was listening to James McKay. Nobody thought a kid from rural Saskatchewan who'd learned to fix tractors with baling wire could solve a problem that had stumped the best minds in the Royal Navy. The numbers told a grim story. The Royal Navy was losing 35% of their fuel capacity before a single ship fired its engines in combat. 35%. That meant for every 100 gallons loaded in port, only 65 gallons actually powered convoy escorts across the Atlantic. The other 35 gallons simply vanished through evaporation, spillage, or degradation during the crossing. 1 in every 3 convoy escort missions failed to maintain position at all. The destroyers simply ran dry in the middle of the Atlantic, their fuel exhausted, their precious cargo stranded in the killing zone, while German U-boats circled like wolves. The Royal Navy was bleeding fuel, and the bleeding was getting worse. Without fuel, the entire Battle of the Atlantic teetered on the edge of collapse. Destroyer escorts sat silent in port for lack of gasoline. Patrol aircraft couldn't be positioned to cover convoy gaps. Supply ships went without protection because the escorts carrying them never had enough range, because the jerry cans carrying fuel kept losing their contents before anyone could burn it. Admiral Karl Donitz understood this perfectly. He watched Allied convoys crawl across the Atlantic like wounded animals, their escort destroyers falling behind, running out of fuel, leaving the merchant ships exposed. Every failed escort gave him another day, another mile, another convoy to sink. James McKay was nobody special. He'd grown up on a wheat farm outside Moose Jaw during the worst years of the Depression. His father had taught him to fix combine harvesters using fence wire and prayers because new parts cost money they didn't have. School ended when James turned 14. His family needed him full-time on the farm. There were crops to bring in, equipment to maintain, and no money to pay for help. But James understood engines the way some people understood music or mathematics. He could listen to a tractor cough and know exactly which valve was sticking. He could look at a broken piece of machinery and see how to make it work again using nothing but what he had in the barn. When war came, James enlisted on his 18th birthday. The Navy tested him, found he could barely read a technical manual, and sent him to Halifax as a mechanic's mate. Not an engineer, not an officer, just a seaman who cleaned tools and watched fuel drip onto the ground while his superiors argued about carburetor specifications. That's what he was doing in Halifax in November 1942, maintaining equipment, watching gasoline evaporate, and wondering why nobody seemed to care that they were losing a third of their fuel before ships ever left port. The Navy cared, of course. They cared desperately. They had assigned their best petroleum engineers to solve the fuel loss crisis. Men from Imperial College and MIT, experts in fluid dynamics and chemical engineering, worked night and day on the problem. Their solution was to modify the fuel pump pressure systems, redesign the valve timing to reduce flow turbulence, install pressure regulators that would minimize cavitation during transfer operations, optimize the pump seals to prevent micro-leakage during storage. They tested dozens of configurations. The changes helped a little. Fuel loss dropped by maybe 6% on a good day. But the changes were expensive, time-consuming, and required skilled machinists to install. Each modification cost over $200 per ship, required a certified marine engineer, took 3 days per vessel to complete. And 6% wasn't enough. Not nearly enough. Other experts recommended special fuel additives, chemical stabilizers mixed into the gasoline to reduce evaporation and improve storage stability. The additives worked in laboratory tests, but shipping millions of gallons of special chemicals across the Atlantic was impossible. The supply chain couldn't handle it. The convoy ships that were supposed to carry the additives couldn't reach their destinations because they kept running out of fuel. It was a problem that ate its own solution. High Command considered abandoning long-range convoy escorts entirely. Maybe the destroyers couldn't be fixed. Maybe the Royal Navy would have to accept shorter patrol ranges. Maybe Germany would simply win because Britain couldn't figure out how to transport gasoline across the ocean without losing a third of it to thin air. James Mackay watched all this happen. He watched engineers work on fuel pump modifications. He watched officers argue about chemical additives. He watched convoy escorts leave Halifax with full tanks and return weeks later with horror stories about running dry 400 miles from port. And James noticed something that nobody else seemed to see. The gasoline was evaporating in the jerry cans before it ever reached the ship's fuel tanks. Those 20-liter steel cans, stacked by the hundreds on deck, sat in the freezing Atlantic wind all day. The metal heated and cooled with the weather. The gasoline inside heated and cooled with it. Cold fuel contracts, warm fuel expands. Temperature changes created pressure.
The standard jerry cans had a large vented cap to prevent pressure buildup. Made sense in theory, but those same vents let fuel vapor pour out constantly. By the time ships reached mid-Atlantic, the jerry cans held maybe 14 liters instead of 20, and the gasoline that remained had degraded from constant exposure to air and temperature swings, making engines run rough and hot. James mentioned this to the senior petty officer in his unit, a grizzled machinist who'd been fixing Navy equipment since before James was born. The petty officer barely looked up from his work. "Kid, we got MIT engineers on this problem. You think they haven't considered the jerry cans? The problem is in the fuel pump systems. That's where the experts are focused. Get back to work." But James couldn't let it go. He'd grown up on a farm where gasoline was precious. His father had taught him to store fuel in sealed metal drums, kept cool in the root cellar and out of direct sunlight. Never in open containers where it could evaporate. Never in exposed locations where temperature would degrade it. James had spent his childhood making 5-gallon stretch to do 10 gallons work because buying more meant going without something else. And now he was watching the Navy waste fuel like water, focusing on complicated pump modifications while ignoring the simple fact that half their gasoline was evaporating from jerry cans before anyone even tried to burn it. The problem wasn't the fuel pumps, James thought. The problem was how they stored the fuel itself. But he was 18 years old, with a 9th grade education, and who was going to listen to him? James couldn't sleep. Every night he lay in his bunk thinking about those jerry cans sitting on deck, leaking precious fuel into the Atlantic wind while engineers fiddled with pressure regulators. He kept remembering something from his childhood, a memory that wouldn't leave him alone. His father used to store gasoline in sealed metal drums during harvest season. Not just any drums, but drums with tight rubber gasket seals that he'd scavenged from an old steam engine. He'd bury those drums in the ground behind the barn where the earth stayed cool year-round. The gasoline lasted longer that way, didn't evaporate, didn't degrade in the prairie heat. His father had learned that trick during the Great War, when every drop of fuel mattered. What if the Navy was solving the wrong problem? What if those brilliant engineers were looking in the wrong place entirely? James started thinking about the jerry cans themselves. The standard 20-liter steel cans had a large vented cap at the top to let air in as fuel poured out, and to prevent pressure buildup and temperature changes. Made sense in theory, but those same vents also let fuel vapor escape constantly. Cold nights created condensation, hot days created expansion. Evaporation never stopped, and 20 liters became 14 liters without anyone noticing until the cans felt too light. James's idea was radical in its simplicity. Don't modify the expensive fuel pump systems, modify the cheap jerry cans. Make the vent opening tiny, much smaller. Add a spring-loaded valve that would open in pressure when someone poured fuel but keep vapor from escaping the rest of the time. And do something about the temperature swings themselves. Find a way to insulate the fuel even when the can sat in freezing wind for days. He started experimenting in secret. After his regular shifts ended, he would stay late in the maintenance shop, working by lamplight when everyone else had gone to sleep. He pulled a damaged jerry can from the scrap pile, one that had been dented beyond regulation and condemned for regular use. Using a hacksaw and a metal file from the workshop, he reduced the vent opening from 3 inches down to a 1/4 inch, just a tiny hole. Then he needed a valve, something that would open under pressure when someone poured fuel, but seal tight the rest of the time. James found a small spring in a box of assorted hardware, one pulled from a scrapped truck clutch. He measured its tension carefully, compressing it with different weights until he found it needed exactly 2 pounds of pressure to open. That was perfect. Enough pressure to let fuel pour smoothly, but not enough to let vapor escape during normal storage. He fashioned a simple check valve using the spring, a thin rubber gasket he pulled from a broken water pump, and a small metal disc. The valve sat in the reduced vent opening, held closed by spring tension, opening only when internal pressure built up during fuel dispensing. But James wasn't finished. He needed to address the temperature problem directly. Walking through the maintenance yard one evening, he noticed strips of rubber insulation that had been removed from steam pipes during a boiler repair. The rubber was thick, about a 1/4 inch, and it had interesting properties. Rubber didn't conduct heat well, it insulated. He cut strips of rubber insulation and glued them to the inside of his experimental jerry can, using waterproof marine adhesive. The rubber lining covered the interior walls completely, creating a thin barrier between the steel exterior and the gasoline inside. 3 weeks passed. James worked every night modifying jerry cans one at a time using scrap materials he scavenged from around the depot. Nobody paid attention to what the kid was doing in the corner after hours. He modified 12 cans total. Each one got the reduced vent opening, the spring-loaded check valve, and the rubber insulation lining. He tested the valves obsessively, making sure they opened at exactly 2 pounds of pressure. Too tight and fuel wouldn't pour properly. Too loose and vapor would escape. He filled practice cans with water, timed how fast they emptied compared to standard jerry cans. His modified version actually poured 15% faster because the check valve opened fully under pouring pressure, but the rest of the time it sealed tight. He filled 2 of his modified jerry cans with actual gasoline and set them on the dock next to 2 standard cans, also filled with fuel. After 48 hours of direct exposure to November weather, freezing nights, warmer days, constant wind, he measured the fuel levels. The standard cans had lost nearly 3 liters each. His modified cans with rubber insulation had lost half a liter. I could feel the temperature difference just touching them. Less temperature swing meant less expansion, less evaporation, less waste.
Now came the hard part. James needed to convince someone to actually test his modification on a real convoy escort. He approached his immediate supervisor again, the same petty officer who had dismissed him weeks earlier. This time, James brought data. He showed temperature measurements, evaporation tests, comparison charts. The petty officer looked at the numbers, looked at the modified jerry cans, and shook his head. "This isn't your job, Mackay. You're a mechanic's mate, not an engineer. You want to change how the whole Royal Navy handles fuel. That's above your pay grade, way above." But there was one person who might listen. Lieutenant Commander Robert Harrison ran convoy escort operations out of Halifax. James had worked on Harrison's personal Jeep several times, and the older man had always been decent to him, never talked down to him the way some of the other officers did. Harrison was also desperate. His destroyer escorts kept running dry mid-Atlantic, and men were dying because fuel wasn't getting through. Desperate men take chances they wouldn't normally take. James found Harrison at the operations desk on December 3rd. He brought 2 modified jerry cans and his notebook full of measurements. Harrison listened, which was more than anyone else had done. He looked at the check valve, tested it with his thumb, watched how it opened under pressure. He picked up both cans, felt the weight, shook them to hear the gasoline slosh inside. Then he asked James a simple question. "How much did this cost you to make?" James did the math in his head. Scrap rubber, scrap spring, scrap metal, a bit of adhesive. Maybe 50 cents per can, sir. Maybe less if we're buying materials in bulk instead of scrounging scraps. Harrison whistled low. The MIT fuel pump modification costs over $200 per installation. Tell you what, Mackay, I've got a destroyer heading out tomorrow morning. 6-day patrol and back. I'll load your fancy jerry cans. We'll see if they make any difference." That was all James needed. He stayed up all night preparing 40 modified jerry cans for Harrison's ship, checking every valve, every seal, every detail. The destroyer HMS Skeena left at dawn on December 4th, 1942. Standard procedure was to measure fuel levels before departure and after return. Skeena carried Harrison's test batch of 40 modified jerry cans on the port side deck. The starboard side carried 40 standard cans for comparison. 6 days later, the ship returned. The standard jerry cans had lost an average of 28% of their fuel to evaporation and spillage during the journey. The modified cans lost 8%. 8% instead of 28%. And the fuel that remained was noticeably cleaner, less degraded by temperature exposure. Skeena also reported better engine performance throughout the patrol, less engine knock, less overheating. The higher quality fuel meant the destroyers ran smoother and more efficiently. Harrison took the results straight to Rear Admiral Murray, the officer responsible for all convoy operations in the Western Atlantic. Murray was a career officer who'd built his reputation on efficient logistics. He was also watching his carefully planned convoys fall apart because of fuel losses he couldn't control. When Harrison showed him James's numbers, Murray made a decision that could have ended his career if it went wrong. He ordered a full field test. 20 ships, half equipped with standard jerry cans, half with James's modifications. A 2,000-mile route designed to simulate real Atlantic crossing conditions. Every vessel's fuel consumption tracked and measured precisely. It took James and a hastily assembled team of 6 mechanics 2 weeks to modify 800 jerry cans. They worked around the clock, installing reduced vents, spring-loaded valves, and rubber insulation, testing each can to make sure it met James's specifications. The maintenance depot became a jerry can factory, producing 60 modified cans per day. The test convoy rolled out in late December 1942. When it returned in early January 1943, the results were undeniable. Ships using modified jerry cans arrived with 68% more usable fuel than the control group. 68%, not 6% like the MIT fuel pump modification, not 12% like the chemical additives would have provided, 68% more fuel, which translated directly into extended range, into longer patrol times, into destroyers that could actually protect convoys all the way across the Atlantic. Before James's modification, Royal Navy convoy escorts averaged 1,800 nautical miles of operational range when you counted all the losses from evaporation and degradation. Only 65% of every gallon loaded in Halifax did useful work at sea. The other 35% just vanished. After the modification rolled out in February 1943, that same escort system achieved 3,000 nautical mile range with only 8% loss in transit. The effective range increase was 67%. James had promised to stop the bleeding, and the math proved he'd actually done it. Murray didn't wait for permission from London. He couldn't afford to wait. Every day of delay meant more convoys lost, more sailors dead, more German U-boats that would escape. By March 1943, over 5,000 modified jerry cans were in service across the Western Atlantic. Mechanics worked in shifts, converting standard cans to James's design as fast as their hands could move. The modification was simple enough that any mechanic with basic tools could do it in the field. No special equipment needed, no complicated procedures. Just cut the vent smaller, install the spring valve, glue in the rubber lining, test the seal, and move on to the next can. By May 1943, over 50,000 modified jerry cans were deployed across all Atlantic operations. The Royal Canadian Navy heard about what one of their mechanics had accomplished and adopted the modification immediately. The U.S. Navy was slower to believe it, skeptical that something so simple could work so well. But by June 1943, even the Americans were converting their fuel cans to the Mackay design. The impact showed up in major operations. During the convoy battles of spring 1943, Allied destroyer escorts could pursue U-boats 40% further than in previous engagements. That extra range meant the difference between German submarines escaping and being forced to surface where aircraft could sink them. U-boat losses spiked. Convoy losses dropped. German intelligence noticed the change by April 1943.
Donitz's staff officers were puzzled by reports that Allied escort destroyers had suddenly extended their operational range far beyond what was previous analysis suggested was possible. Ships that should have run dry were reaching positions that had been considered out of effective escort range.
The Royal Navy officially recognized what James had accomplished in July 1943. They designated it the Mackay Seal in technical manuals and supply documents. Every new jerrycan produced in Allied factories after August 1943 incorporated James's design as standard equipment. The modification became so routine that sailors didn't even realize their fuel cans were special. They just worked better than the old ones, poured faster, didn't leak as much, kept gasoline cleaner. In September 1943, James Mackay received a field commission to lieutenant. An 18-year-old farm mechanic with a 9th grade education became an officer because he'd saved the Royal Navy millions of gallons of fuel and possibly saved the entire Battle of the Atlantic. The enemies of innovation had been so sure they were right. The MIT engineers knew that fuel pump systems were the problem, so they focused on pressure regulators. The petroleum experts knew that chemical additives was the answer, so they developed expensive stabilizers. The officers knew that a mechanic's mate with no formal education couldn't possibly solve a problem the experts had failed to crack. They were all wrong. They were wrong because they'd forgotten to question their assumptions. They'd forgotten that sometimes the biggest problems have simple solutions. And simple solutions often come from people who aren't trained to think in complicated ways. James didn't overthink it. He just remembered how his father stored gasoline on a Saskatchewan farm during the Depression, and he asked himself why the Navy wasn't doing the same basic things that any sensible farmer would do. Keep the fuel cool. Keep it sealed. Don't let vapor escape. It wasn't rocket science. It was common sense. The kind of common sense that comes from growing up poor and learning that waste is a sin because every wasted gallon means doing without something else you need. An 18-year-old farm mechanic with barely a 9th grade education saw what seasoned engineers missed. He looked at a jerry can and asked a question nobody else had thought to ask. What if we're using this wrong? That simple question extended Allied convoy range by 67%, helped turn the tide in the Battle of the Atlantic, and reminded everyone who paid attention that expertise without curiosity is just educated blindness. The next time someone tells you that's how we've always done it, remember James Mackay working alone in a maintenance shop after midnight. Remember him watching fuel evaporate into the Atlantic wind and refusing to accept that waste was inevitable. Remember him proving that common sense and careful observation can beat credentials and authority every single time. James Mackay never accepted the answer that things couldn't be different, couldn't be better, couldn't be fixed with simple tools and clear thinking. He changed the course of World War II with some scrap rubber, a truck spring, and a bit of common sense wrapped in the stubborn conviction that problems exist to be solved, not to be accepted.